So thanks a lot for the invitation. So I would much rather have been in UCLA than be here online. I think we all feel the same. These conferences are there to discuss, and I'm sure at some point we will kind of catch up again. But it's difficult to use this this platform to really exchange ideas. But I would like to talk about the only good thing that came out of this whole Corona kind of business for me is that finally you have time to sit down and work on problems that are hard. And one of these problems that we had for 10 years basically is an algorithm, is like a DMRG algorithm for dealing with continuous matrix product states. This turns out to be an extremely challenging problem, and we did not make any progress for 10 years. But then the Corona came, and it was possible to basically sit down for like 2 months and do nothing else than work on that problem, and that was apparently enough to crack it. So I hope I will be able to kind of explain a little bit what it's about. Wait, let's see. Okay, overview. Some recent developments in tensor networks that I wanted to highlight because they are kind of nice pictures. It also fits extremely well actually with the talk of Ian. Then I want to talk about continuous tensor networks. I think this is something that most people are not familiar with. And then actually also how you optimize, how you deal with them, how do you actually work, how can you do DMRG with functionals instead of with matrices. So I give you all, this is of course the completely generic overview of tensor networks. So they provide a faithful representation of quantum many-body wave functions of even in the continuum and thermodynamic limits. So they are very well tailored for strongly correlated systems. They're real space methods, and they basically the essence of these tensor networks is that they model the way the entanglement is routed throughout the system. So depending on whether you're a 1D or a 2D or a 3D system, you really want to use you want to understand the entanglement structure and then make use of it to come up with some interesting variational class to simulate this and to actually extract all the interesting information. And this basically, for me at least, the appeal of tensor networks is that it has like a double feature. So on the one hand, they provide a theoretical framework for understanding the structure of critical topological phases of matter in terms of these entanglement degrees of freedom. And I think this makes actually this DMRG-like methods that Steve White discovered completely unique in somehow the realm of all the numerical methods. So it is really not just providing you a method for simulating the things, but also it provides you a way of understanding the physics behind this. In that sense, it's I can, from my point of view, it's very similar to what people in the beta ansatz did. So in the beta ansatz, there's a beautiful theoretical framework that can also be used for numerics, but it goes really beyond what is possible with beta ansatz because we can clearly also deal with non-integrable systems. So in this talk, I will be mostly kind of concerned with the computational methods. Basically, how do you deal with them? How do you simulate these kind of systems? So let me kind of give you a very kind of short movie of the typical physics problems that you can do, and that I don't know how to solve any of these in any other method. So what you have is basically a Schwinger model. This is QED and 1D, and you take some test charges and put them as a distance away from each other, and then start seeing how does the entanglement grow in between them as a function of the distance. So this is basically the full confinement, deconfinement kind of picture of charges in QED and all this. All of this can be studied perfectly well using very simple kind of NPS methods. You just have to solve ground state problems with given pinned test charges somewhere, and you solve for the ground state and start seeing how does the entanglement depend on the distance, and then you can understand confinement, deconfinement. I think this is wonderful, and this is really completely impossible to do with any other kind of method. A similar kind of problem that actually gave rise to lots of follow-up works, especially in the context of quantum simulation, is like trying to understand excitation energy. So what are the elementary excitations, the elementary particles on top of the vacuum in systems with long-range interactions? And what you see is that typically as a function of the power of somehow the long-range interactions, so either you get topological trivial or non-trivial excitations as being the lowest lying excitations. And it turns out that this has a huge huge effect on the physics that people actually observe in the lab doing this. So these are the kind of problems that I think are wonderful. So this is really, you can just do this using these MPS methods. So a different kind of method or a different problem that a student of mine solved last year, Maarten van Damme, is basically trying to understand wave packets. How do they scatter? What does that mean, actually, a scattering phase? So what you do is take a spin 1 Heisenberg model, prepare 2 elementary excitations. Okay, so we prepare some kind of elementary particles on top of the vacuum, and you will basically let them scatter with each other. And what you will see is that, well, you have basically two particles. Well, they have both spin 1, and of course, when they kind of come together, you will have both a spin 0, spin 1, and spin 2 sector. And what you see is that indeed there is a delay somehow, depending on whether you're in the spin 1 sector, spin 0, or spin 2 sector. There is a delay, so you can really understand the scattering phase. You can just simulate this in real time using somehow these DMRG type of methods. And I think these are kind of wonderful kind of things. So you can actually then plot what is this shift that you see in this plot, and you can compare this with other methods for calculating scattering phases. And indeed, this kind of fits perfectly well. So this is these are the kind of things that make sense and have never been able to, people have never been able to do anything like that with any other method. Okay, so the last kind of highlight that I wanted to give is a paper of my student Bram van Ecke that actually will should have appeared today on the archive, but apparently he was like one minute too late with the deadline, and therefore it will only appear tomorrow. But it's actually very much in line with the talk of Ian. It's about scaling data and collapse in critical systems, when you kind of simulate critical systems, but really in the continuum limit. So what is kind of extremely interesting is you start simulating continuum theories, is that there's two kind of notions of criticality that emerge there. There's both somehow the UV kind of central charge that emerges, but also the IR central charge. And exactly somehow when your system is tuned to the critical point for your field theory, you get actually beautiful interplays between UV physics, IR physics. All of these things come together, and by making use of nice scaling laws, very much in spirit of what Ian does, we can really start kind of determining critical points or the critical kind of parameters of the system to a precision that is really many orders of magnitude better than any other method by which you could kind of easily you could try to kind of do this. So this is basically the motivation. These are the type of problems we want to solve. Let me now actually go, well, okay, this is indeed, for example, this critical alpha C. Somehow there's a renormalization independent critical point for this theory. It's like the critical temperature for the Ising model, but in this particular case, it's a parameter alpha C, and this is basically the new result that we got, which is really kind of much better than let's say state-of-the-art Hamiltonian truncation methods or Monte Carlo methods. Is really kind of much better. But these are the kind of problems we want to solve, and for which we need continuum theories. We really want to go to the continuum. So that's why somehow we wanted to ask: is it possible? How much mileage can we get by immediately starting with continuous tensor networks, by working with tensor networks that are immediately defined in the continuum? Okay, so what? Sorry, what is the main motivation? Well, the spin chains or the Hamiltonians that we simulate using DMRG are of course always effective theories. Okay, so if you take, for example, a Bose-Hubbard model, okay, like in an optical lattice, the Bose-Hubbard model is an effective model that you obtain by ignoring basically the higher bands. Okay, so there are higher bands in your theory. You say, well, the probability of occupying them is very small, so therefore ignore it. I make an effective model out of kind of spin systems, and I want to, well, I just do this and I create an effective Hamiltonian. Well, this is certainly not always justified, especially not if you kind of want to simulate indeed these experiments using optical lattices or atom chips in which actually the continuum is there. Okay, these are really continuum theories. We would like to, and for these theories, it turns out that it's not easy to decide how to discretize them, how to put them on a lattice. But so what is this is basically the motivation. There's lots of experiments done in the continuum. The nature is at the end at the deepest level is in the continuum. So why can't we kind of immediately come up with methods that work in the continuum to start with? But there's also like some very fundamental questions or some fundamental issues that we need to solve. It's like for especially in the context of atomic physics, there's this very famous Gross-Pitayevsky kind of equation that is basically has a monopoly in describing BEC and interact like really kind of these cold atomic gases. But it turns out that for low dimensional systems, if you confine your atoms to an effective one-dimensional trap, this is actually not kind of very good, because this Gross-Pitayevsky is a mean field approach. So for this, you need to take into account correlations, and there are now kind of obvious ways of taking into account, of constructing somehow quantum versions of Gross-Pitayevsky that actually take into account these correlations. So this is exactly what we will do, actually using these continuous matrix product state methods that I want to kind of introduce here. So there's also fundamental questions and problems like in simulating relativistic quantum field theories. Like if you want to simulate a relativistic quantum field theory, you have to somehow you put this on the lattice, you kind of have a lattice cutoff, and the question is this lattice cutoff, how is this similar to an entanglement cutoff? But there's also kind of fundamental problems that once you put things on the lattice, you get this famous fermion doubling problem. Can you kind of overcome this by working or by immediately using variational methods in the continuum? Are there kind of really things that are different once you put them on the lattice? And indeed, this is an extremely well-known problem, especially in the lattice QCD community, that many features in, let's say, in 4 dimensions cannot be reproduced on the lattice in 4 dimensions. You have to go to a 5-dimensional lattice to get chiral fermions or to get some kind of chirality in the way you want it in your system. So it turns out that these are kind of really kind of fundamental problems that are there because you put these things on the lattice, and therefore these are all motivations of actually trying to do it immediately in the continuum. And of course, there's besides somehow the fact that there's a physics issue, there's also fundamental kind of reasons why we are interested in continuum theories, but there's also aesthetic reasons that once you have analytic results and the functions are always much nicer than like derivatives are always much nicer than difference equations. No, so that's why at the end the physics that we do, the equations that come out of it will be much more easily interpretable if we deal with derivatives than with differences like we typically do on the lattice. Okay, so how does how does this work at the end? So this is something that we did now 10 years ago. So this was actually it took a very long time to actually get this to work, but to get the fundamental or the theoretical foundation for that turned out to be very easy. So all of you have already kind of seen matrix product states now during this conference and during the previous kind of introductory kind of talks to many times. So it turns out that somehow these matrices that you have matrices that determine your matrix product state. Okay, the MPS is the trace of the product of matrices of that kind. And if you kind of want to simulate a field theory, something like a system that has a finite density of particles, let's say, then most of the time you want to be in the vacuum. Okay, so the A0 basically means that I'm in the vacuum, I have no particle. But if you have like a particle alpha, a type alpha could be 1, 2, or whatever, if you have many different types of particles, but you say like when I have my physical system not to be 0, but in alpha, I kind of replace my tensor, your main matrix product state tensor, with a square root of epsilon times R alpha, where epsilon is basically the lattice cutoff. It turns out that with such a discretization, such a kind of a way of introducing a lattice cutoff, you can actually take completely the continuum limit. And if you take the continuum limit, this is something that we did in a paper more than 10 years ago, actually, you get basically the continuous matrix product state Feynman, which is nothing more than a path-ordered exponential of sums of local terms. Okay, so these are basically, this is exactly the same. This Q of X and R alpha of X really play 100% the role of somehow your matrices in your matrix product state. They are no different at all. The only difference is actually that here you work in second quantization. So this is like, this is an operator that satisfies commutation or anti-commutation relations. But at the end, the path-ordered exponential is something that, of course, all of you know. A path-ordered exponential is something that emerges when you integrate a differential equation. Okay, so you integrate the Schrödinger equation. What you get is a time-ordered exponential. Well, in terms of a time-ordered exponential, exponential, what you get here is a path order exponential. And this is really because this path ordering is nothing else than telling you in what order I have to multiply these matrices. The path ordering is exactly the ordering that will give rise somehow, that gives you exactly the same rule as you would have in the matrix product state limit when you put it on the lattice. So at the end, you have a wave function immediately in the continuum. So the Hilbert space is basically infinite dimensional. You have like on every kind of space in X, you can have a boson or a fermion, or it doesn't matter what kind of particle you have. And the variational parameters that you have are these d by d matrices Q of X and R of X. Okay, so what are the typical Hamiltonians that we can deal with, that we are interested in? So, for example, this is the Lieb-Liniger model. Okay, so this is like the kinetic energy. So people in physics, they always take in some sense you get rid of the 1/2m. You just write somehow this Hamiltonian because, of course, we can all absorb this in constants. So what you have is a kinetic energy term. So this is nothing more than somehow the p squared term, kinetic energy of a non-relativistic particle, and you have a point interaction term. So psi dagger, psi dagger, psi psi. That means that if somehow two particles if two particles are meeting somehow at point X, you get an energy penalty of C. So this makes actually this theory interacting. It turns out that this specific Hamiltonian is integrable. Okay, so it's the famous Lieb-Liniger Hamiltonian, and that's why, of course, you can compare somehow the results then with exact results because it's an integrable system. But it turns out that using these matrix product state rules, it's very easy to calculate all expectation values as a function of these matrices R and Q. Okay, there's very similar formulas as the ones that you have in DMRG. The only difference is that when instead of sums and difference equations, what you get is kind of time order or path order exponentials. But in many ways, it is exactly the same kind of equations that you get in the continuum. So if you would have to guess what are the formulas, if you kind of would take DMRG in a continuum, you would probably write down exactly these formulas. Okay, so what you get is things like covariant derivatives with like the commutator of Q and R, or in some sense telling you what is the kinetic energy. So I see that Joe has a question. Please.
Yeah, I'm just a little confused as to what you're taking a limit and what is staying fixed. So let's say we have some matrix product states. So we have a bond dimension, a physical dimension, and a number of nodes. What are you taking a limit of here?
Yeah, so you have field operators, so you may work in second quantization, and on the lattice, you basically have some commutation, anti-commutation relations for these field operators that are not basically, of course, a delta function in a continuum, but are basically just functions, just a delta function for a discrete variable. So it turns out that to take the limit, you have to multiply these field operators on the lattice with 1/square root of epsilon. Okay, just from dimensional reasons, it turns out to be what happens. And indeed, if you do this, these field operators, somehow this delta function, the discrete delta function, becomes indeed a delta Dirac function because you multiplied actually both this psi and the psi dagger with 1/square root of epsilon. So, and that is exactly what is needed to get this. And it turns out that this can be compensated then by putting this epsilon and square root of epsilon in these matrices. And then if you do this, so if you kind of both do the scaling of the field operators and these matrices, and then take the limit of epsilon going to 0, turns out that there's a well-defined that you can write down exactly the formula or somehow the exact expression of that state in the continuum using somehow the second quantization. But I did not want to kind of really go to the details of this because it would take actually this too far in this half an hour. I don't really have time. But in some sense that's the spirit. You both have to renormalize your field operators and basically the lattice spacing. And if you do this in a consistent way, then you get this. Turns out that this is nothing new. Now, people in beta ansatz community do exactly the same. That's how they go from spin chains to field theories. Okay, so turns out that, for example, this Lieb-Liniger Hamiltonian can be understood as a limit of the XXZ Hamiltonian. Okay, it's a quantum spin chain. If you kind of work at a certain specific limit of a certain density where the density goes to 0, and you kind of take the XXZ and take exactly the same limits, you get this Hamiltonian. So there's nothing. This is really not really kind of ingenious or anything special. It's a very natural thing. Of course, it's very nice that the matrix product state language allows to do that. But anyway, so you can calculate all all the expectation values in a very standard way, and well, you can then get basically the energy as a function of this Q of x's and R of x's. And now we want to optimize these Q and R of x's to kind of do variational calculations. So the first thing.
Can I try one more time to the same question? So where does this object live? Your new object.
So
what's the ambient space?
So the Hilbert space is actually the many-body Hilbert space. So what you have is a continuum. So you have a line L2 of you just have a continuum, let's say an interval between minus L over 2 and L over 2. And on every kind of parameter, on every kind of location X, you can have an arbitrary number of bosons. Okay, and the field operator psi alpha X, psi, let's say psi dagger beta y of x acting on the vacuum of your theory creates a boson at location y of type beta. That's what it basically does. So it's a many body. So on every kind of location in the continuum parameter, you can have an arbitrary number of bosons. Of course, in the physical situation, we will have a finite number of bosons on a finite interval. So that means that almost everywhere, somehow your space is empty. And that's indeed why basically your matrices almost everywhere look like the identity, except with somehow a certain kind of epsilon. And this epsilon will control, of course, somehow this is the lattice spacing. It will control the density, the fact that you have a finite density of particles. But the Hilbert space is in some sense, you can have an arbitrary number of bosons on every kind of x coordinate, and therefore it's a many-body Hilbert space, of course, that you need. So the dimension of that Hilbert space is, of course, well, it's humongous, no? So you cannot even write it down. But of course, the physics is being done, and this is, of course, exactly the same physics that is described in, let's say, in beta-ansatz community using Blinger. But somehow, typically, of course, in the beta-ansatz community, what you have is a U1 kind of charge. You fix the number of particles. So typically, in the beta-ansatz community, you say, I have exactly, let's say, 40 bosons in my trap, and I write down a wave function for these 40 bosons. In principle, if you were second quantization, that's not needed. You can have superpositions over different particle numbers. But we'll come back to this actually later. Is that kind of clear, Joe?
I'll ask you later.
Yeah.
Yeah, so there's one more question, please.
Sure.
Jonathan.
Can I ask a related question? So for discrete systems, we know that the MPS approximate well the ground state. Are there results like when it takes limits, these continuous MPS also approximate ground state of this field theory?
I did not completely understand your question, but I thought it's the question whether these are good representations of the ground states. Well, it seems so.
Are there like theorems of this kind?
No, there are. It's much harder to find theorems of that kind because most of these theories that you're interested in are actually critical theories. And therefore you will have to do some scaling anyway. So it's not that. So the typical theorems about MPS are about approximating ground states of gapped systems. But most of the systems that you're interested in the continuum actually have massless excitations and therefore are kind of critical. But nevertheless, by doing a scaling in somehow the parameter in the bond dimension of these things, it turns out that we can extract lots of interesting physics. And it turns out our experience, so this is certainly not a proof, but the experience is that actually you can get around with much lower bond dimensions for continuous matrix product states than with normal MPSs. And the reason is that in the continuum, because you have this nice smooth kind of continuous functions, there's much less UV physics that eats up lots of entanglement. Okay, so there's lots of entanglement actually going on in normal spin chains that has to do with the UV physics of your spin chain that is not there anymore once you took the limits to somehow a continuum theory. But about theorems, there's almost no theorems. We don't even know exactly what the parent Hamiltonian is for a CMPS. This is a long-standing open problem in this field of continuous matrix products. So the theory is much less developed for sure. Okay, so there are examples. Okay, so people did lots of simulations with this. So these are like simulations of deep linear type of Hamiltonian where we have longer range interactions. It turns out that actually using this CMPS, so there's also different types. When you have fermions, you have bosons. So people did lots of simulations and extracted literature parameters and this. So it turns out that indeed these things work. Okay, so they really allow you to extract physics that is very, very hard to get with other methods. But let's actually kind of, one thing that we were very excited about, this is actually was a PhD student of mine, Damien Draxler, who kind of looked at this, is actually looking at excitations on top of somehow the CMPS. What are these particles? And it turns out that these particles or that MPS methods are extremely good in understanding or capturing dark soliton excitations on top of the vacuum, that these are things that all pop up very naturally in the CMPS language. But I would be happy to talk about this later. But from a more fundamental point of view, we really wanted to understand also whether this allows you to overcome basically some fundamental issues in simulating relativistic field theory. So there's this very famous kind of papers of Feynman in which he was looking for variational methods for simulating relativistic field theories, and basically in this paper or this talks that he gave about that topic, he said that he felt it should be possible, but he didn't really understand how to do it because there was some like an inherent contradiction that if you're interested in a relativistic field theory and in continuum limit, what you do if you turn this into a variational problem, you really have to concentrate on the UV physics, and the UV physics is exactly the physics that is irrelevant because you're interested in the long range physics, but there's much less energy to be gained by the low energy physics, of course the long range physics, than the UV physics. That's why he basically said, well, this is doomed. There will be never a variational principle that will work for continuous kind of theories, for relativistic theories, and that have both kind of that have UV divergences. And it turns out that actually these CMPS methods, as we showed actually now 10 years ago, but now there has been kind of much more work on that, allow you to overcome that. So this is really the very, very first time that people come up with interacting ansatz for continuum theories by which you can actually simulate continuous like interacting field theories. So in that sense, it's really a big deal. And for this, I really wanted to highlight a paper that just appeared, let's say, last month from Antoine Tierwa, in which he indeed kind of builds somehow now on top of this CMPS, he builds somehow a relativistic kind of, he uses a variational method using CMPS, but he has kind of a bit of a slightly different way of constructing this, in which somehow these field operators A of x are not the usual ones in which you have like a 1 over square root of somehow k of x. No, that's kind of a non-local way of doing this approximation. And by this, he really kind of solves all somehow the requirements or all the problems that Feynman identified in using relativistic or kind of continuum functionals as variational methods. So this is really kind of a big deal that these CMPS methods allow you to overcome somehow all these naive kind of obstacles for using the variational method for field theories. And this is, we hope, the first step to actually do this at the end for much more complicated field theories and maybe things like even QCD or will be amenable to variational methods. But of course, this is a very far kind of future dream. But let me actually go. I don't know exactly how much time I have left.
I just wanted to give you a notice that you're almost out of time, basically. But there were a lot of questions, but maybe if you could...
yeah, but I already had like 5 minutes of questions, so let me kind of try to take like 2 minutes to go to the real meat of the talk, because I have not actually talked about what we solved last year. So as I said, somehow, so all these problems that I talked till now, they were actually the translation invariant case. Okay, they are kind of the case in which I have a finite system and I kind of put the same matrices, this Q and this R, I make them independent of X, and then I kind of just solve this as somehow a big thing in which I impose translation invariance. It's like a uniform matrix product state. Of course, there's many problems in the lab that actually for which the boundary conditions are very important. If you kind of put one of these optical lattices in the lab, you have the boundary condition. You have a non-trivial, a non-translation invariant potential. You have boundary condition. You have all these kind of things. So to actually to use this in the lab, you need to be able to simulate finite systems. So in 2017, after like 7 years, we were able to write down basically the equations that would govern a non-translation invariant kind of thing. So these are basically the quantum or the matrix version of these Gross-Mitaevsky equations, where you kind of basically write down the time-dependent variational principle for this CMPS. So you get actually very, very complicated formulas. But then it took us another 4 years to actually integrate them. Okay, and this is basically the issue that we were able to solve in this paper that I referred to in the first case. That is, from our point of view, at least a big breakthrough, because this is the kind of problem that we wanted to solve and that turned out to be extremely hard. So how do you actually kind of work with such a CMPS if you what is the analog of DMRG for the CMPS when you actually have a non-translation invariant system? You have a system with boundary conditions and so further. So it turned out that the big trick was to combine ideas from finite element analysis and backwards differentiation as is used in machine learning kind of communities. So basically what you do is make an ansatz, a piecewise linear ansatz for your kind of tensors Q and R. You make them, and of course the grid that you choose, you can choose this adaptively and so further. But then somehow the key idea was to integrate these equations or somehow the corresponding CMPS equations, but do this exactly. So for this, you basically, even if you interpolate this, you need actually to have the left and right reduced density matrices, just like in DMRG. And for this, you basically do an exact Taylor series. So you kind of construct a Taylor series expansion for these rho and sigma, the left and the right reduced density matrices, but you do this such that it is kind of completely exact up to machine precision. Okay, so you need a few Taylor coefficients in between your grid points, and then you'd use backwards differentiation techniques to calculate the exact gradient. And actually putting all of these things together is a big, is lots of work, and but it works perfectly. And now we can really start studying things like linear gases in boxes with, for example, the Dirichlet boundary conditions. You do this, you get these fantastic oscillations. You can actually calculate, like say, the energy. You can see actually that indeed the number of particles in such a box for this particular parameters was like 33.999. So you see that even if you don't impose a U1 symmetry, actually what comes out is something with an extremely well-defined particle number. You can calculate Casimir energies, boundary energies using these methods. So these are really kind of opening up these things. So even to calculate things like that using beta ansatz are extremely hard. Of course, now we can do this for interacting theories, for theories that are not integrable and so further. So we did other things. So like you have an external periodic potential, exactly like people have in optical lattices. Now you can calculate densities, energies, kinetic energies. You can compare actually with methods like other methods like LDA methods on top of beta ansatz. And turns out that really for interesting or for relevant parameter regimes, the results that we see are really kind of very, very far from what you would kind of do with other methods. So I think I'm already kind of too much over time. So this is actually one dimension. So the question is now what happens in higher dimensions? We have been thinking a lot about this. I would be very glad to talk about this, but let me conclude here by saying that that actually finally after all these years, actually the continuous matrix product states are coming up to age, and we are starting to be able to use them to simulate actual experiments. And actually the code that we have for reproducing all these results here is actually will be put online. I can send you a link because the code such that you can actually run all these things yourself. Because actually to implement this yourself is very hard. But there is an open source code in Julia that allows you to actually run all these experiments and these simulations yourself. So thanks a lot for your patience.